Hello, my name is Jimin LEE from the KGSEA Math Circle, and I'm going to give a brief presentation about Boolean algebra and logic gates. Let's start with the basics of computing systems. Computers store or communicate data in a unit called bits, which is the smallest unit of information. A single bit is always one of the two possible binary states, and the two values are determined when electricity flows or when there is no flow of electricity. So when electricity flows, the value is commonly denoted as 1, high, on, or true. If there's no flow of electricity, the value is commonly denoted as 0, low, off, or false. For the purpose of this presentation, I'll be frequently using the two values 1 and 0. And similar to numbers, Boolean values can also be passed through operations. And these operations can also be expressed in a digital circuit with logic gates. So let's start off with the most simple one, and the most simple logic operator is not. So not x returns the value that is the opposite of x, which is 1 if x is 0 and 0 if x is 1. In algebraic notation, not x is denoted as such, and the logic gate is a triangle with a circle on the right side. Next is the and not and operation. A and B returns a value of true if both A and B are true, and false if otherwise, as also shown in the truth table. Similarly, but in the opposite way, not and returns the opposite value of A and B, which is 1, 1, 1, 0 for this truth table. And operators are commonly denoted with multiplication, or just written together as AB, or a logical conjunction symbol. And in the logic gates, and not and operators look like this, as shown on the slides. Next is the or and not or operators. A or B returns a value of false if both A and B are false, and true if otherwise, as shown in the truth table. In these combinations of A and B, A or B returns the value of 0, 1, 1, and 1. The algebraic notation is commonly denoted as A plus V, or a logical disjunction symbol, and the logic gates looks like as follows. And the XOR operators returns the value of true if A and B are different, and false if otherwise. So if A and B are both 0 or both 1, A XOR B is 0, returns a value of 0. And if the A and B values are different, the XOR values are returned as 1. The notation of XOR is an addition symbol with a circle around it, and the logic gates looks like this shown on the slides. Okay, now that we know the basics of Boolean operation and logic gates, I'll be demonstrating an example problem. So there's a logic circuit shown on the slide here, and the two questions are: express the circuit below in a Boolean expression in terms of A, B, and C, and number 2, construct a truth table for this circuit. So to express the circuit below in a Boolean expression using these three variables, we first need to convert the logic gates that are shown in the visual method into algebraic expressions. And this is what I have noted above in the image. This logic gates converts to not, this logic gates converts to XOR, this logic gates convert to not and other logic gates are converted that way as well. Rearranging this circuit into a Boolean expression with parentheses to separate each logic gates, it returns the following expression, which is not A multiplied by B XOR C, and the complement of that multiplied by B XOR C added to C. Okay, to construct a truth table, we can use the expression deduced in the above question, which is shown here on the slide. And then extending the truth table with A, B, and C, we could construct a truth table value for expressions that are part of the entire Boolean expression. So for example, not A can be created as a separated column, B XOR C can be created as a separated column, just as we did for not A. And if we continue this for all parts of the Boolean expression, we can eventually deduce the final truth table on the rightmost side of the slide, which is 0, 0, 0, 1, 0, 1, 1, 1. Okay, and there's another concept called minterms and maxterms in Boolean algebra. Minterms are the product of all variables in the function in which each variable appears as its true or complement form. If the variable takes the value of 1, we would use the truth form, which is just normally a. Otherwise, we could use the complement form, which is not a. The minterm values are commonly noted as a lowercase m with its index noted in the subscript. So max terms are the sum of all variables in the function, where each variable appears as its true or complemented form, similar to minterms. But in the opposite way, if the variable takes a value of 0, we would use the true form. And otherwise, we would use the complement form, which is the opposite of the true form. And notation-wise, we denote max terms as capital M with its index noted in the subscript. Okay, since the description might be difficult to understand on its own, we'll look at some examples. So let's say we have a truth table here and a function value that returns these following outputs. To calculate the minterm, we would look at the values of A, B, and C and then multiply them together. So for row 1, since all A, B, and C take the value of 0, we use complement values for all of them. So M0 is complement of A times complement of B times complement of C. In the second row, so as C takes the value of 1, we would, instead of the complement form, you would use its original form, so just C without the complement sign. So M1 is complement of A times complement of B times C. So if we continue this for all the other rows, we get this result for all minterm values for all combinations of A, B, and C. So proceeding on to the max terms. So max terms, as explained before, is the sum of all variables, and we would use its original values of the variable if the variable takes the value of a 0. So for M0, a max term, we would add the original values for all A and B and C. So M0 equals A plus B plus C. And for the second row, since C takes the value of 1, we would use the complement value for the variable C. So M1 equals A plus B plus complement of C. So if we continue this for all the other rows, we get the results like this. So using these minterms and max term, we would construct Boolean equations in SOP and POS form. So SOP form, which is a short form of sum of product form, is an expression that is a logical sum or of minterms when their output is 1. So in notation, we would say that F is equal to the summation of M with the minterms indices denoted as follows. And the product of sum form, which is POS form, is a logical product of max terms with the output of 0. So the notation is like this, which is the sum of max terms, which is the product of max terms. And POS and SOP forms are used to simplify complex logical expression. So let's look at an example. So let's say we have a truth table like this. To create a sum of product form, we would only consider the rows where F equals 1. For each row where F equals 1, we could deduce its minterm, which is A complement times B times C complement, and these other values for the other rows. And then to create the sum of product form, we will sum all the products together, which yields the following equation. So we could carry out a similar process also for the product of sum form, but only considering the rows where F equals 0. So for each row where F equals 0, we could deduce its max term, which is A plus B plus C for the first row, and these other two values for the other rows. And then we could get the product of all the sums together, which yields the following equation on the slide as the sum of product of sum form for the following truth table. And another way to simplify Boolean expressions is using Carnot maps, which is often called as K-maps in short form. And it is a table-like visual tools which is used to simplify Boolean expressions. So some properties of K-maps is that they're commonly used with 4 or less variables. Each cell's position is represented by a minterm from the combination of variables. So for this example with 3-variable K-map, we would usually say this cell is represented by the value 0, 0, 0. And the value of each cell is the value of the expression for that input combination. So we use the F value to fill in the cells. And the labeling for the K-maps follows a gray code in which only one variable changes between adjacent cells. This will become more clear with a visual representation on this slide. So let's say that we have a truth table like this and a min-term like this. So we could construct a 3-variable K-map as shown in the slides. Each row, the column values represent the A values and the row values represent the values for B and C, and each cell is filled in with the value of F. So for example, 0 when ABC is 0, 0, 0, also 0 when ABC is 0, 0, 1, also 0 for when ABC is 0, 1, 0, 1, 1, and 1 when ABC is 0, 1, 0. And note how adjacent cells only vary by 1 bit. So looking at these top row, the values change from 0, 0 to 0, 1 to 1, 1 to 1, 0, in which only one digit of the 2 digits change as we proceed to the adjacent cell. And to convert K-maps to Boolean expressions, we could follow the steps listed on the slides. So first, group the adjacent ones into rectangles, and each rectangle must be a power of 2 in size and must be as large as possible. Number 2, write a simplified expression for each group. So first, determine whether an output of values in the cells is independent or dependent of a certain value. If the outcome is dependent of the variable, include the original term as it is, if it's 1, and the complement if otherwise. And step 3 is to combine the simplified terms through summation. And this yields the final equation in SOP form. And to derive the expression in POS, we could instead group the adjacent zeros, use complement values, and switch the product and sum. So we'll look at one example for this. So we have the example of the K-map, 3-variable K-map that we used above. So one group that we can make is the red group, which is a group with 4 cells. Since all cells have A as 1 and are independent of values of B and C, which is basically the same meaning as the B and C can be whichever values between 0 and 1, we could deduce the value for the red group as simply as A. And another group that we can create is this blue group, which is a group with 2 cells. These cells are independent of the values of A, and these cells all have a value of B as 1 and C as 0. And since we have B as 1, we could use the original value of C and C as original value of B, and C as 0, we could use the complement value of C. So overall, we could deduce the expression B times complement of C. So adding these values for the 2 groups, the K-map can be simplified to the equation F equals A plus B times the complement of C. And to convert this into the POS form, we could follow the similar procedure of grouping into sizes with a power of 2. And then instead of summation, we could multiply the value that are deduced for the 2 groups. So as shown on the slides, the red group can be simplified to A plus B, and the blue group to A plus the complement of C, and thus the K-map can be simplified to the equation F equals A plus B times A plus the complement of C. So let's have to solve a practice problem. So given this truth table, the first question is to express the following truth table in SOP and POS form. And the second question is to minimize the 2 above expressions using a K-map. So I'll give a moment to read the questions and the truth table. Okay, to convert this into SOP and POS form, we'd use to first deduce the min terms and max term for each row. So this is the same for what we did before in the example problems. And by doing so, and by only using the min terms values for F equals 1 and max term values for F equals 0, we can deduce the SOP equation as F equals complement of A times complement of B times complement of C plus complement of A times B times complement of C plus A times B times complement of C. And the POS form can also be derived similarly as F equals A plus B times not C times A plus not B times not B plus not C times not A plus B plus C times not A plus B plus not C times not A plus not B plus not C. So moving on to the K-map, we could construct the K-map as follows based on the above truth table. So let's first look at the SOP form. So looking at the red group, the A can take the value of either 0 or 1, B is fixed to 1, and C is fixed to 0. So looking at only the fixed values, we can deduce the expression B times not C. And since there are no other groups, the SOP form can simply be denoted as F equals B times complement of C. So for POS form, we have two groups. The first group is in the first group with 4 cells, A and B can be either 0 or 1, and C is fixed to 1. So similarly, looking only at the fixed values, we could use the expression the complement of C. So looking at group 2, A is fixed to 1, and B is fixed to 0, and C can either be 0 or 1. And so looking only at the fixed values, we can get the expression not A plus B. So for simplified POS form, we could use the function F equals complement of C times complement of A plus B. Okay, to summarize the content of the presentations, data and computer systems are binary and can either take the value of 0 or 1. Boolean data can be processed through logical operators such as NOT, AND, OR, and XOR. Boolean expressions can be expressed as circuits. There's minterm M and a maxterm capital M for each combination of variables. Truth table can be converted into sum of products SOP or product of sum POS forms using minterms or maxterms, and Boolean expressions can be simplified using K-maps. And this is the end of my presentation. Thank you.